See you. They're just going to hear my voice in my hand. All right, so we're going to call these notes salts versus molecules. We spent a ton of time on salts, right? We spend a ridiculous amount of time on salts. Now we're going to spend a fraction of a second on molecules. All right? You ready? Okay. Salts are ionic compounds, right? What kinds of elements make up salts? Metals and nonmetals. And remember what happens? The metal loses electrons to become a positive ion. The nonmetal gains those electrons to become a negative ion. And essentially what you end up with is two little magnets that stick to each other magnetically, right? We showed that with mechanisms. Well, what the heck is a molecule? If a salt is ionically bonded, a molecule is covalently bonded. It's a covalent compound. So it's a more specific term for that kind of compound. All right, what kinds of elements make up molecules? Two nonmetals. All right, so here's an example. H2O. Does that qualify? Yeah. In this particular case, we're going to treat hydrogen as if it was a nonmetal, right? What about CO2? Is that a compound? A molecule? Is that molecular? Yeah. What about this? Is that a molecule? No. Okay. So these are molecules because both of the substances in that particular compound are considered nonmetals. Hydrogen, I hate using hydrogen, but I have to because it's so commonly used. You can actually use it either as a metal or a nonmetal, depending. All right. To figure out whether it's going to bond ionically or covalently, you really have to look at its electronegativity value and see what its difference is with the electronegativities of the two elements here. You have to subtract them from one another. And if they are greater than 1.7, you call it a salt. If it's less than 1.7, you call it a molecule. Yeah, what? Exactly. What do you mean? Sometimes it'll go like up to 2. Yeah. But you have to look at an electronegativity difference to figure out which way hydrogen's going to go. All right? In this case, it's going to be covalent. All right, anyways, how do you use Lewis dot structures? To depict the formation of a molecule. Well, we're going to do the same way we did the last time. We're going to start by drawing the atoms and their dot structures and trying to figure out how to fill in each other's valency, right? So let's use water as the example. So what are the elements in water? Hydrogen, right? And oxygen. There's actually 2 hydrogens in water, right? Because the formula is H2O. 2 hydrogens for every 1 oxygen. How many valence electrons are there in each of these hydrogens? 1. So I'm just going to draw it with a dot. I'm going to draw that one with 1 dot as well. How many valence electrons does oxygen have? 6. So I'm going to draw 1, 2, 3, 4, 5, 6. Are the hydrogens happy? No. Is the oxygen happy? No. Why not? They don't have full shells. All right, now, in contrast to the salts, right? So in the salt, hydrogen would flat out give its electron to the oxygen. That hydrogen would flat out give its electron to the oxygen. We're not going to flat out give the electrons. Because if hydrogen were to give its electron to oxygen, what's it left with? Nothing. Right? Is that good? I don't want to be left with nothing. Is there a better way? Yeah. They can share electrons. So instead of flat out giving it its electron and becoming an ion, right, the better scheme is that they end up sharing electrons instead. So they don't form ions at all. All right? So again, the hydrogen needs 2 electrons to be stable. The oxygen here needs 2 more electrons to get 8 to be stable. Let me move this up so you can see what I'm writing. Oxygen could take the electron from hydrogen, could flat out steal it from it. But it would leave hydrogen with nothing. And that's bad. What prevents it? It's the electronegativity difference. The pull of the hydrogen nucleus is still strong enough to retain it. So it's like having a bully try to come and steal your toy from you, but you're still strong enough to put up a fight. Okay? So instead, hydrogen chooses to share its electron with oxygen. And likewise, oxygen will share its electron with hydrogen. To make all 3 atoms stable. What you're trying to do is you're trying to make as many guys stable as you possibly can in one sitting. Don't just make one guy happy, make all 3 happy. And so you do that by sharing. And so, do you notice that I didn't draw anything with brackets here? Why not? Because you only draw brackets when what forms? Ions. We didn't make ions here. So instead, what we do is we just draw all of these 3 letters together with the dots in between, showing the electrons that are being shared. All right? So these shared electrons have a very common name. It's called the covalent bond. Am I off screen? Yeah? Those shared electrons are called covalent bonds. And normally you don't leave the picture like this. Instead, we end up redrawing the picture like that. What did I do? Yeah, Sam? All right, so I replaced these 2 dots with a line, right? So what that line represents are the electrons in the bond, the 2 electrons that are in that bond, right? And what about these dots on top? Those are just unbonded electrons that are still floating around in that p orbital for oxygen in order to make it complete and stable, right? So the line here again are the 2 electrons in the bond, and then those here are unbonded electrons that are just there to fill the valence. All right, so the mechanism doesn't look much different than before, does it? The only real key distinction is this intermediate step, we don't draw things in boxes and brackets because we don't make ions. Instead, what we just do is put the dots together, okay? No ions form for these things, right? So no ions form. This is really critical. No ions form. And so if no ions form, do they conduct electricity? No. All right, so I cannot conduct electricity through sugar. What does that tell me about the elements in sugar? They're all nonmetals. How are they bonded? Covalently. I can conduct electricity through molten magnesium chloride. What does that tell me about magnesium chloride? It's got ions because it's ionically bonded. Okay? All right. let's talk about some properties really quickly. What are some properties of molecules? As I just mentioned, they don't conduct electricity. They don't form ions. Salts are in what state at room temperature? All of them. Solid. What about covalent things? They're usually gases or liquids. Very few of them are solids. They can be, but not that many. Think about taking a spoonful of sugar and a spoonful of salt and putting them in a pot on your stove and turning up the heat. Which one melts on you first? Sugar. Melting points of molecular compounds are significantly lower than salts. It takes a lot of energy to melt a salt. You can do it, but it's like 500, 600 degrees. Sugar you can melt with very little heat. Here are some examples of molecules. H2O, CO2, CO, NH3, C6, H12O6. In all cases, look at the elements that are in that formula. Where are those elements on the periodic table? Both of them come from where? Do they both come from the upper right-hand corner of the periodic table? Yes, they do. Okay? Yes? Ooh, that's a great question, Morgan. Couldn't it be reduced? No. Because we do not reduce formulas for these things. Okay? Write that down. Formulas for molecules are not, and put that in capital letters, not reduced. We only reduce ionic things. That was a great point to make. All right, so let me show you how to name them. Give you a couple of examples. All right, so P4O10. This is called tetraphosphorus decoxide. Okay, let me give you another one. OF2, oxygen difluoride. SO3, not to be confused with SO3 2-. That's a completely different substance altogether that has a charge of 0. This is sulfur trioxide. What am I doing? I'm telling you how many there are in the name. Did we do that before with salts? No, because with salts we had to think about charges. All right, so here's what you need to know. You need to know these prefixes. All right? 1, the prefix for 1 is mono. 2 is di. 3 is tri. 4 is tetra. 5 is penta. Anyone want to take a guess at 6? Hexa, like a hexagon. 7, hepta. 8, octa. 9, nona. And 10, deca. What did I do with the name? So tetraphosphorus decoxide. Well, I looked at the formula. How many phosphorus do I have? 4. What's the prefix for 4? So I put 4 phosphorus, so tetraphosphorus. How many oxygen did I have? 10. What's the prefix for 10? Decoxide. So what I did is I took the number of atoms, or the prefix that tells me the number of atoms of the first element, and then I took the name of that element, tacked it on, right? And then I did the prefix of the number of atoms of the second element, and I tacked that onto the name of the second element, and in the end, what did I put? "-ide." There is one little detail you should know, and I'm going to highlight this. You should too. Mono. There's something funky about mono that you have to remember. Take a look here. OF2. How many oxygens were here? I didn't put mono in the name. You never use mono with the first element. But you do with the second element. So like, take a look at this example, CO. What is that? How many of those do I have? 1. What's the prefix for 1? Mono. But am I allowed to use mono with the first element? No. So just go ahead and name that. This is carbon. How many of those do I have? What's the prefix for 1? Am I allowed to use mono with the second element? So this is carbon monoxide, the stuff that kills you that comes out of your tailpipe. All right? So much easier, right? You don't have to know anything about charges. All you have to know is these prefixes, and you should know a lot of these prefixes because those are the same prefixes you use in geometry when you're describing polygons, right? Okay, there might be a couple that you have to memorize, and I will tell you in particular, students mess this one up a lot, the tetra, and they mix up the hexa and the hepta a lot, so just be mindful of those. But let's take a look at some formulas, and let's practice this. N2O4. Di what? Nitrogen. How many oxygens? 4. So this would be tetroxide. If you wrote tetraoxide with an A and O, I wouldn't be upset. But technically speaking, you're supposed to drop the A. All right? How about this next one? We did this one, right? Already? How many sulfurs do I have here? 1. What's the prefix for 1? Mono. Am I allowed to use mono with the first guy? No, so we're just going to say sulfur. How many oxygens here? 3. So trioxide. Next one. Nitrogen. No. Monoxide. Okay, next one. Nitrogen dioxide. Next one. AS is arsenic. So this is di-arsenic pentoxide. PCl3. Phosphorus trichloride. Okay, CCl4. Carbon tetrachloride. H2O. Don't say water. Dihydrogen monoxide. Don't forget, you use mono, you use it for just the second element. SCF6. Selenium hexafluoride. Okay, carbon dioxide, what's that formula? CO2. Carbon monoxide, what's that formula? CO. Diphosphorus pentoxide. P2O5. Dinitrogen monoxide. N2O. Silicon dioxide. SiO2. Carbon tetrabromide. CBr4. Sean. Guys. Sulfur dioxide. Phosphorus pentabromide. Five. Iodine trichloride. Nitrogen triiodide. Iodine, I3, and dinitrogen trioxide. So for covalent things, you just read them straight off the name, right? There's no charges that you have to memorize. You only do the whole business with the charges for ionic things. And that's why I save this for last. I really save this for last because in past years when I've started with this, then students get lazy on me and they want to use this for everything. You can't do that. So like for instance, NaCl, they would want to tell me that that was called sodium monochloride. You don't do that. Those are not the rules you apply for those compounds. You only use these prefixes for this stuff. For substances that are made with two nonmetals, okay? We have a completely different set of naming rules. Does anyone have any questions? Sammy, you had a question?
So this for sugars or
all covalent molecules are named this way. So that's why it's really critical that when you're naming, you have a periodic table in front of you. So you can look at the elements that are in the compound, figure out where they land on the periodic table, and whether you should be doing the crisscross business with the charges that you've memorized, or whether you just read the name straight and tell me how many there are using these prefixes. It really is critical to know, well, where is this element? Are they both coming from the right side of the periodic table, or is one coming from the metal side, one from the non-metal side? Okay, how much time do we have? Not enough for a quiz, huh? Man, what a shame. Tomorrow, 2 quizzes.